Good morning, everyone. My name is Xuejing Yuan, and I'm going to talk about our paper, CommanderSongs, a systematic approach for practical adversarial voice recognition. This is the outline of our report. Automatic speech recognition, saying ASR for short, is the technique that allows computer to understand human voice. Thanks to deep learning, ASR systems have been developed quickly in recent years, such as Alexa, Google Assistant, Siri, Cortana, and iFlyTech. Based on the ASR system, intelligent voice control devices, namely IVC devices, have been widely used in our daily life. In the help of them, smart lock, automobile, Twitter, and so many IoT devices, as well as social networks, are better connected. Although these devices have brought great convenience for us, their security threats our property, even our lives. Traditionally, attackers can set up malware, transmit virus, and wireless signals to attack them. Based on the vulnerability of deep learning, researchers proposed the adversarial sample by carefully adding perturbation on an image. The crafted adversarial sample can cause a machine learning classifier to misbehave. Last year, researchers succeeded in making adversarial traffic sounds in the physical world. It means that the adversarial sample has already got so many achievements on the image recognition. This inspired us the motivation to attack the artificial intelligence by voice command. As we know, voice is a broadcast channel, and IVC devices are always listening. Therefore, attackers can issue voice command to cheat them. During the past several years, researchers introduced excellent work using noisy-like sound and ultrasound to attack IVC devices. For example, hidden voice command and dolphin attack. However, the noisy hidden voice command maybe get a human realization of the abnormality. The dolphin attack needs a proper transmitter, and it uses the vulnerability of hardware rather than deep learning. Recently, researchers constructed fabulous target audio adversarial samples to cheat an end-to-end ASR system, but it is limited when the sample is played over the air and can't be transferred yet. So can we design an approach that is using normal sound to make a physical world attack? In detail, we want to automatically generate adversarial samples so that they can practically attack ASR system without human realization. We would like our attack to be surreptitious, can be spread and transferable to attack more commercial applications. Consequently, we present our attack to embed a voice command into a song and name it as CommanderSongs. We take the advantage that it can be spread by TV, computer, and radio, so that it can attack the ASR system when humans are listening to music at home, outside, or even in a car. For example, if we are enjoying CommanderSongs from the radio, the IVC device recognizes the command in the sound that wants it to set the temperature to 24 degrees, and it will execute the command. There are three challenges we should overcome. Firstly, the commands in the song should be unnoticeable to ordinary people. Secondly, CommanderSongs attack should be effective in the presence of electronic noise from speakers and the background noise. Finally, the attack should be remotely deliverable and can be widely spread. Now I will introduce our approach. Usually, the audio is a wave file, and it can be input to the ASR system directly or broadcast over the air. We take the automatic speech recognition system as an API. Therefore, we divide our approach wave to API attack and wave air API attack. We name them as WTA Attack and WAA Attack for short. The first one, WTA Attack, aims at crafting a song to make it can be decoded as the target command by ASR system. The crafting degree should be as little as possible to escape from human realization. To complicate the physical world attack, the second step, WAA attack, should be effective when command song is played by a speaker and recorded by a microphone. We take a popular open source platform Kodi as the ASR system. There are two main models in Kodi, namely acoustic model and language model. The acoustic model is trained by deep neural network, and it is used to represent the probability between features and phonemes. Phoneme is the smallest unit composing a word. Every phoneme has several states, and each state corresponds to a different probability density function. The language model is described by weighted finite state transducers, and it is a probability distribution over a sequence of words. The decoding procedure is as follows. Firstly, the audio is separated into a sequence of frames, and the features of every frame are extracted. Based on the trained acoustic model, those features are taken as the input of the deep neural network to compute the probability for every state. Combine the result with the language model, the transference between hidden Markov model states is calculated, and the largest log likelihood words sequence is the decoded result. In Kodi, the probability density function is indexed by PDFID, which also exactly indicates the column number of the DNN output matrix. In addition, transition ID is used to uniquely identify the HMM transition. Therefore, a sequence of transition IDs can identify a phoneme. Furthermore, a sequence of transition IDs can identify a word or a sentence. For example, the word echo contains 3 phonemes. The red box highlights them, and each phoneme corresponds with a sequence of transition IDs. This table is the segment of the relationship among the phoneme PDFID and transition ID. By referring to it, we can obtain the PDFID sequence corresponding to the decoded transition ID sequence. We set it as the target PDFID sequence. To make Kodi decode as the echo, we need to make sure that the probability of this target PDFID sequence is as large as possible. We set A as the DNN output matrix of the music audio, and the highest probability PDFID of the S frame is Mi. Gxt is a function to get the vector M from A. On the other hand, we decode a legitimate audio including the command by Kodi and get its transition ID sequence. We look up that table to find its corresponding target PDFID sequence and define it as a vector B. Through detailed analysis of the DNN output matrix, we observed that if M approaches or equals to B, this audio can be decoded as the command, and we define it as a PDFID sequence matching method. Therefore, we get our objective function. And our WTA attack is successful. Then we use gradient descent to craft an original audio into the command song, namely xt plus delta t, which satisfies the objective function. Hence, our WTA attack is successful. However, as the craft degree of the WTA attack samples are too small, they can't keep the attack effectiveness because of the influence from the speakers and the background in the real world. To realize the physical world attack, we modify the WTA approach by adding a noise model of the background and the speakers, so that the command song can be robust for over-the-air attack. We build this model by comparing the recorded audio with the original one. However, it needs us to access to the devices. Therefore, we put forward random noise as the noise model. Luckily, this model is effective for diversity speakers and recorders. Therefore, our WAA attack is successful. Now let's look at the evaluation of our CommanderSong attack. We randomly download some music from the internet to do the experiments. The music includes rock, rap, popular, and soft music. The results show that for WTA attack, we can craft all of them as the CommanderSong to carry any commands. For the WAA attack, we choose 3 kinds of speakers to play our CommanderSongs, and use the iPhone to record them. The distance between the speaker and the phone was set at 1.5 meters. It can be seen that the effectiveness of WAA attack is influenced by the speakers, and the success rate can up to 96% for the JBL speaker. To evaluate human comprehension of the CommanderSong, we made a survey on Amazon Mechanical Turk. 204 persons participated in our survey. Some questions regarding each audio need to be answered, such as whether they have heard the original sound before, whether they heard anything abnormal than a regular sound. The 4 options are no, not sure, noisy, and words different than lyrics. If choosing noisy option in this question, they would answer where they believe the noise comes from. While if choosing words different than lyrics option, they were encouraged to write down those words and answer how many times had they listened to the song before they recognized the words. Generally, for the WTA samples, compared with rock, popular, and rap music, soft music proves to be the best candidate to carry the command. None of the participants could recognize any words of the desired command in the adversarial samples. Talking about the WAA attack, on average, 40% of the participants believed the noise was generated by the speaker, while only 2.2% of them thought the noise from the samples themselves. In addition, less than 1% believed that there were other words except the original lyrics. However, none of them successfully identified any words, even repeating the sounds several times. We chose the iFlyTech ASR system as the target of our transfer, since it processes 70% of the market in China. In particular, iFlyRec is an service online to convert audio to text, and iFlyTech Input is a popular mobile voice input application. The results show that our WAA attack is transferable on iFlyTech. Those adversarial samples containing commands like open the door and good night can achieve greater transferability on both platforms. In addition, our attack is still effective if the CommanderSong is spread by internet and radio. Now let's watch how it works. Firstly, we inject the command in a video and spread it with a link. We have a phone and a speaker nearby it, and enable the after enable the application on the phone and play the video, the decoded result is shown in the phone. Yes, we can see the decoded result is open the door. This is the command we inject in the CommanderSong. In addition, this attack is effective for many kinds of phones, such as iPhone, LG, Huawei, Xiaomi, and so on. We explain the CommanderSong attack as follows. Suppose the dark blue circle is the set of audios that can be recognized as commands by Cody, while the light blue circle and the pink one represents the set of audios can be recognized as a command and songs by human respectively. At first, the original sound is in the pink circle, meaning that neither Cody nor human can recognize any command inside. WTA Attack slightly modifies the sound so that Cody can recognize the command, while humans still cannot. After noises are introduced to generate a command song for WAA attack, it will fall into the light blue area step by step. In the end, it can be recognized by humans as well. We put forward two methods to defend the attack. Audio turbulence defense is to add a noise to the input audio before it is received by the ASR system, and check whether the resultant audio AI plus AN can be interpreted as other words. As the features of the legitimate command and WAA attack audios are too strong, this method can defend WTA attack. Then we propose the audio squeezing defense method, that is, reduce the sampling rate of the input audio and compare the decoded result. The features of the downsampled WTA and WAA attack audios are too weakened to keep the proper results, but the legitimate command audio can maintain the same results still. Therefore, the audio squeezing method can defend the command song effectively. In conclusion, based on the vulnerability of deep learning, we craft a song to carry a voice command and define it as a command song. This is the first systematic approach to generate such a practical attack against the automatic speech recognition system. The command song attack can be transferred to flight attack, even spread through the internet and radio. And the command in the song is surreptitious. That's all. Thanks for your attention. Next, I will be happy to take any questions.
Any questions? So I have a question. So first, most of your experiments are done in the mobile phones, right? Have you tried whether this attack will work on different IoT devices like Google Home, Amazon Alexa?
The final target is of our work is to attack more IVC devices. Firstly, we have attacked the flight attack already, and this is an ongoing work. We have achieved some steps in, but maybe it can be because so many IVC devices are black box for us. It's difficult to transfer the other platforms, and we will try it better.
Kevin from the University of Chicago. Very nice talk. So I have a question about the methodology of the WTA attack. So it looks like the methodology is quite similar to Nicholas Carlini's adversary examples on the deep learning models. But however, his approach failed to attack over the air. So what do you think is the major difference between your WA attack? What makes it work over the air? Is it because embedding into a song, or is it because of the background noise you added to the model?
Actually, our attack isn't only can inject the command in the song. It can inject any audios. Compared with Nicholas' attack, our WTA attack can't transfer to other platforms, while the WAA attack, considering the noise, the speaker's influence and the background noise, so that they can better transfer and can be effective for the over-the-air attack.
Another quick follow-up is in his attack, he used a CTC loss, and have you considered that in your methodology?
Yes, we'd like to combine the CAUDI and the CTC together to make a more approach.
Okay.
Thanks.
Thanks.
Hey, I'm from University of Florida. In this case, you targeted CalD DNN, and you target a specific portion of that architecture. Maybe I missed it, but do you think that it would work for other architectures, maybe end-to-end architectures, or do you have any insight in that?
Sorry, could you please repeat your questions?
Yeah, so do you think the attack methodology would work for other model architectures, or ASR architectures? Do you think iFlyTech just uses CalD DNN, so maybe it just works because they're the same architecture, or do you think it would transfer to other architectures as well, the model architecture?
Do you mean the iFlyTech, the iFlyTech is similar with the CAUDI?
Yeah, do you think that they're the same architecture, or maybe they're different architecture and it just transfers to different architectures easily, your attack?
Actually, iFlyTech is a black box for us. We don't know the theory of it. Maybe maybe our attack can transfer to iFlyTech. In some degree, maybe they are using the similar features, or some other deep neural networks are similar. But I'm not sure.
Okay, great, thank you.
Thanks.
Hi, Atul Prakash from University of Michigan. So on the defense work that you presented towards the end of the presentation, so like similar defenses have been tried on image analysis, like reducing the resolution of the image, for example, as a way to defend against adversarial attacks, but they've been shown to be broken. I'm kind of wondering, have you tried tweaking your attack algorithm to account for the defenses that you proposed and see if you can still find the attacks, or whether that work needs to be done? Like, I'm kind of thinking that maybe the defenses will get broken, potentially get broken, given the history on the image side, image analysis side.
Sorry, do you mean your defense can?
Yeah, so there was a defense, I think you talked about, if you go back a couple of slides, on the defenses. Yeah, this one, like you proposed these two defenses. Have you tried tweaking the attack algorithm and see if it can overcome the defenses? Like modifying your attack algorithm?
Sorry, I can't understand.
So I think the question is that, for example, the feature squeezing defense actually for the image actually is shown to be broken. So for this case, have you tried to change your attack to try to test whether it can bypass this defense or not?
The audio screening defense.
Right.
Like, yeah, it's like to destroy the features.
Okay,
yeah.
So maybe we'll discuss offline. Thank you.
Thank you.
Thanks, everyone. So our question for lunch is that, is IoT security interesting? After you send all the talks. Thank you. Thank you, everyone.